Hey everyone. In our previous video, we were discussing nucleophilic addition to ketones and aldehydes, and we were discussing commonly used nucleophiles. So down below you can see we categorize them by their kind of main atom. So we have nucleophiles that contain oxygen, nucleophiles that contain sulfur, nitrogen, hydrogen, and carbon. Now, in this video, we're going to focus on oxygen nucleophiles and the reactions that they go through. All right, so let's start with water. So what happens if we react a ketone with water as our nucleophile? Well, we end up forming something called a hydrate. So hydrates have two alcohol groups bonded to the same carbon. Now, what if we did the same reaction but with an aldehyde? So we'll use formaldehyde here. Well, we get something similar. We get two alcohol groups, but instead of two alkyl groups down below, we have two hydrogens from our aldehyde. Now, when we perform these reactions, what we find is that the yield of the first reaction is only 0.1%, and the yield of the second reaction is 99.9%. Why do you think that is? Why is the second reaction more favorable, or why does it favor products? So remember in the last lecture, we talked about how aldehydes are less stable than ketones, right? So aldehydes only have either one alkyl group or no alkyl groups in this case. So the carbonyl carbon isn't as blocked and it's more easily accessible. But additionally, it isn't stabilized by those alkyl groups through hyperconjugation. So aldehydes are less stable and they react more quickly. But again, if you were to react an aldehyde with water, you end up with a hydrate. So let's look at two mechanisms for this type of reaction. Let's look at the case where we have acidic conditions, and then we'll look at a case where we have basic conditions. So we'll use formaldehyde again, and we're going to start with acidic conditions. So we have acid hanging around. What's the first step in this reaction? So remember, if you have acidic conditions, the first step is protonation of oxygen. All right, and then we said that our nucleophile is water. I'll just draw the full Lewis structure for that. Okay, so the oxygen is going to come in and attack that partially positive carbon, and we're moving electrons up to oxygen as a result. So we end up with an alcohol on one side, and then we have our water on the other side. Okay, so what do you think our last step will be? We're going to remove one of those hydrogens on the positively charged oxygen. So we could just use water to do that. We'll probably have multiple water molecules hanging around. But again, notice I am using equilibrium arrows for every step. So we might, go backwards. So we might have to do some tricks to favor the formation of the product. But in this case, our aldehyde is unstable. So we end up forming a lot of the product. So our yield is pretty high. Now also notice that we regenerated our acid, so it is catalytic in this case. Now what if we had basic conditions? What would our mechanism look like? So again, let's start with formaldehyde. And let's draw our water molecule. Now remember, water is neutral. It's not basic. So we have to add a base here to have basic conditions. So let's just show that we have a base hanging around. And that base could be sodium hydroxide, for instance. So what do you think the first step here will be? So remember, bases want to take protons. And what would it take a proton from? The aldehyde or water? Probably water, right? Okay, so that's going to create a stronger nucleophile, the hydroxide ion. And now that nucleophile can come in, attack our partially positive carbon, move electrons up to oxygen, all right. So what do you think the last step will be? We've got to protonate that negatively charged oxygen. So we could just use our conjugate acid that we formed earlier with our base. So oxygen will grab that hydrogen and we'll reform our base and our product here. So the base is also catalytic. So again, you could perform this reaction under acidic or basic conditions, but the mechanisms are slightly different. So again, one thing to notice, under acidic conditions, we have positive charges, and the first step is the addition of a proton to oxygen. Under basic conditions, we have negative charges, and the first step is the base takes a proton from our water molecule. Okay. Now let's look at another example. So let's say we have a ketone, but instead of two alkyl groups, we have halogens attached to each carbon. And we'll just pick fluorine here. And we're going to use catalytic acid in this reaction. All right, and let's compare that to just a regular ketone. Now, the yield of the first reaction is 99.9%. But again, the yield of the second reaction is only 0.1%. So what's going on here? Why do those halogens produce such a strong or such a high amount of product? So what do we know about fluorine? It's very electronegative, right? So that's going to draw electron density away from our central carbon. And that central carbon was already partially positively charged, but if we're drawing electron density away from it towards fluorine, then it's going to become even more positively charged and more electrophilic. So the halogens withdraw electrons from the central carbon, making it more electrophilic. All right, so again, when you're using water as your nucleophile, it is going to create a hydrate. So you have two alcohols bonded to your central carbon, but aldehydes are going to react better or more quickly than ketones. All right, let's look at our next oxygen nucleophile. So what if we react an aldehyde or a ketone with alcohol? So I'm going to draw a ketone, but this could be an aldehyde or a ketone. And we're going to react that with two equivalents of an alcohol. And then let's use catalytic acid here. That's going to end up forming something called an acetal or a ketal, depending on if you use an aldehyde or a ketone. So the product would be an acetal if you're using an aldehyde as your starting material, or a ketal if you're using a ketone as your starting material. And then water is a byproduct. Now, some of the acids that you could use for this reaction are sulfuric acid, phosphoric acid, or toluene sulfonic acid, which we can abbreviate TSOH. And that just looks like the following. And we've used tosyl groups before to make a better leaving group, but you can use this as an acid for your nucleophilic addition reaction too. Now, the reason that we're being so specific about the acids that we use, your acid should be non-nucleophilic. Because if it is nucleophilic, that could create some competition and we might end up with multiple products, right? So we want to make sure that the alcohol is the only nucleophile present and the acid is just there to help the reaction along. It's not there to compete with the alcohol. So let's look at an example or a mechanism for this reaction. Okay, so let's start with our ketone and we're going to use acetone. So that has two methyl groups. And let's say the alcohol we're using is methanol. So pretty simple molecules, right? All right, and then we are going to use catalytic acid. So maybe we're using sulfuric acid, for example. And the first step, again, because we have acid present, we're going to protonate the oxygen. Okay, and let's draw out our two methanol molecules. So in the next step, one of the methanol molecules is going to use its oxygen to attack the central carbon on our ketone, and then electrons will move up to oxygen. All right, and that's going to form the following intermediate. Okay, so we've got a positively charged oxygen on one side and an alcohol on the other side. And then we still have our other methanol molecule hanging around. Okay, so what's going to happen here is the hydrogen that's on our positively charged oxygen is actually going to move over to our alcohol oxygen. So I'm just going to abbreviate that as plus minus a hydrogen. So we're kind of removing the yellow hydrogen and then adding it onto the other side. All right, so now that hydrogen is on the other oxygen. So the reason we did that, or the reason that this happens, is to create a better leaving group. So now we have water on one side, which again is a good leaving group. So now the oxygen on the right-hand side is going to form a double bond, and that's going to kick out our water group. All right, so now we have a positively charged oxygen again. We have formed water as a byproduct. But we also still have our methanol molecule from before. So now the second methanol molecule can come in and attack. Oops. I meant to just draw a positive sign there. There we go. All right, and then we've got our methyl groups down below. Okay, and then we still have that water molecule that's hanging around as a kind of byproduct from before. And now that water molecule can take the hydrogen or deprotonate our positively charged oxygen. So we've regenerated our acid, so that again is a catalytic acid, and that might be H2SO4 or phosphoric acid, etc. We're just writing it as H3O+. And then our product there is a ketal because we started with a ketone. And this would be the same for an aldehyde. So if we showed this same process with formaldehyde, we would, see the same thing, but the two groups on the bottom would be hydrogens instead of methyl groups. Okay, now instead of using these separate alcohols, what if the alcohols were connected to each other? So let's use acetone again. And this time we're going to react it with something called ethylene glycol. So notice that the two alcohol groups are connected by a 2-carbon chain. Again, we're going to use catalytic acid for this reaction. So the first step, we're going to protonate the oxygen at the top. And now the ethylene glycol is going to attack our carbonyl carbon. So let's just say that the oxygen on the left attacks. It doesn't really matter. Okay, so this is going to form kind of an interesting molecule here. All right. Now, in the next step, remember we're going to transfer a hydrogen over to the other oxygen. So again, we can just write that as plus minus H plus to show that the hydrogen has moved. Oh, I'm going to give myself more room since we have that bulky chain. Okay, so that hydrogen has moved over, and now we have a good leaving group. Okay, so now in the next step, the oxygen way out here is going to create a ring system. And that's going to kick out our water molecule. So the oxygen way on the right is actually coming in and attacking the central carbon there. So we're going to end up with the following. And we just formed water as a byproduct as well. So this is one of our cyclic products, right? So this would be leading to a cyclic ketal because we're using a ketone. But if we started with an aldehyde, then we'd have a cyclic acetal or acetal group. All right, so we're just going to remove that hydrogen on that positively charged oxygen. We can use water to do that. So we've regenerated our acid. And now we have our cyclic ketal. So let's do a practice problem just to finish up this lecture. So I want you to try this one on your own first. All right, so how could we go from the starting material to our product? So feel free to pause the video and see if you can kind of work through how to change that ester to an alcohol. And when you come back or unpause the video, we'll go over it together. Okay, so do you remember how to turn an ester into a primary alcohol? So let's just say we have a generic ester and we want to turn that into a primary alcohol. Well, it looks like we need to reduce our ester, right? It also has a good leaving group on it. So if you think way back to last quarter, we can use a strong reducing agent like lithium aluminum hydride, and then some acid to protonate our oxygen at the end. Okay. What about the ketone though? Because we do have a ketone up above next to the ester, right? Wouldn't lithium aluminum hydride also react with the ketone? So how can we make sure that lithium aluminum hydride only reacts with the ester and not the ketone? Well, previously we added ethylene glycol to a ketone, and notice that all of these steps are reversible. So what we can do, and it's okay if you didn't see this part of the reaction because we're learning and I just kind of wanted to give you a slightly challenging problem. So don't feel bad if you were struggling with this. So what we're going to do is we're going to add that ethylene glycol with catalytic acid. And as we saw in the previous example, that's going to create this cyclic ketal, and then we'll also have our ester off to the side. So our cyclic ketal is acting as a blocking group, and it's going to prevent our lithium aluminum hydride from reacting with the ketone. And then later we can remove that blocking group. So water, again, is one of our byproducts. So now we can add that lithium aluminum hydride with some acid there, and that will just react with the ester and not the ketone, and it will turn it into a primary alcohol. And then we're going to remove the blocking group or the cyclic ketal just using water. So water just removes that blocking group. Oops. Removes ketal. And then this step up here adds ketal, which is a blocking group. And then lithium aluminum hydride only reacts with ester due to blocking group. So this is something chemists have to do a lot. Maybe they want to reduce one carbonyl group, but they find that it's also reducing another carbonyl group on the molecule that they don't want to reduce. So you can add these blocking groups and then remove them later. And luckily for us, ethylene glycol will only react with the ketone or an aldehyde and not the ester. So that works out. So just a little trick that you can use in your synthesis problems going forward. I think we'll stop the video there today. Next time we'll talk about nitrogen nucleophiles, and then we'll move on to some other reactions that we can perform with aldehydes and ketones. So I will see you then.